SpaceX and Blue Origin are, they're currently spending just billions of dollars to build the largest, most powerful machines in human history. I mean, we are talking about rockets so massive they literally alter the skylines of their manufacturing facilities.
Yeah, they are absolutely colossal.
Right. But a new report suggests that these towering engineering marvels might actually be, well, massive commercial blunders, like the spacefaring equivalents of the Airbus A380. So today, we're taking a deep dive into a June 29, 2026 Space News article detailing a really comprehensive analysis by the Aerospace Corporation.
Right, and it's a fascinating read.
It really is. The mission of this deep dive is to look past the pure spectacle of these super heavy lift rockets. We need to ask a highly uncomfortable question for you and, well, for everyone following the industry. Is the aerospace sector hitting a catastrophic wall of diminishing returns?
It is a vital question, mostly because the industry is operating on this assumption that has rarely been challenged.
Which is that bigger is always better, right?
Right. Exactly. For decades, the fundamental logic of spaceflight has been that scaling up is the ultimate economic lever. But the Aerospace Corporation report, it really forces us to critically examine the sheer operational reality of these vehicles.
Because things get complicated.
Very complicated. We're reaching a scale where the laws of heavy industry economics just begin to warp. And the financial risks tied to that shift are, frankly, staggering.
Okay, let's unpack this. We're focusing specifically on super heavy lift vehicles, or SHLs. The industry defines these as rockets capable of pushing at least 50 metric tons into low Earth orbit.
That's a massive payload.
Right, so I am struggling with the core economic argument the report is making here. Standard heavy industry economics dictates that if you spread your fixed operational costs over a much larger payload mass, things should get cheaper.
You would certainly think so, yes.
Right, like the launch pad maintenance, the tracking systems, the personnel on the ground. If you lift way more weight, your cost per kilogram to orbit should naturally plummet. So why wouldn't that basic principle of economies of scale hold true just because the rocket gets bigger?
Well, because in aerospace, scaling up isn't just about building a wider fuel tank.
Yeah.
It introduces compounding layers of operational complexity.
So it's not just more metal and more fuel.
Right, exactly. What's fascinating here is how the report identifies the precise mechanical friction points that upend those economies of scale. When you scale a rocket to the SHL class, the physics of managing that vehicle on the ground change dramatically.
Wow, okay. Like how?
Well, you are dealing with exponentially larger volumes of cryogenic fluids, managing the thermal limits of thousands of tons of liquid oxygen and liquid methane while a vehicle just sits on the pad requires massive, highly specialized ground infrastructure.
Oh, I see. So it's not just the cost of the fuel itself, it is the cascading cost of everything required to keep that fuel stable.
Precisely. The marginal costs just skyrocket. You need larger acoustic dampening systems. The water deluge systems required to prevent the engines from literally tearing the rocket apart with their own sound waves are immense.
Tearing themselves apart, that's wild.
Yeah, the acoustics are just that powerful. And the pad refurbishment time between launches extends significantly. Plus, the workforce required to certify the flight readiness of, say, 36 massive engines expands.
Right, because there are just so many more parts to check.
Exactly. The report points out that while your lifting capacity goes up, the cost, the time, and the sheer operational friction demand so much capital. So your per kilogram launch price can actually reverse course.
Meaning it gets more expensive.
Yes. You hit a point of diminishing returns where flying one massive rocket is suddenly more expensive and complicated than flying 3 medium-sized rockets.
That makes a lot of sense. And to frame this, the aerospace report draws a direct parallel to commercial aviation, specifically the Airbus A380.
Ah, yes, the super jumbo jet.
Yeah, so Airbus looked at the booming demand for air travel and applied that exact same economies of scale logic. They said, let's build a super jumbo jet with 2 full passenger decks, cram over 500 people into it, and dominate the market with the lowest cost per seat.
And it was an undeniable engineering triumph. I mean, the A380 flew beautifully.
It really did.
But Airbus fundamentally misjudged the operational and market realities of the time.
Right, because consider the actual deployment of that aircraft. Its sheer size became a massive operational liability. Airbus had to literally force global airports to spend millions rebuilding their terminal gates. They had to reinforce their runways just to accommodate the physical footprint of the plane.
The infrastructure costs were staggering.
Totally. And the boarding process was incredibly slow. The turnaround times at the gates basically killed its utilization rate. And while Airbus was betting on massive hub-to-hub transit, they were completely outmaneuvered by smaller, highly fuel-efficient twin-engine jets.
Like the Boeing 787.
Exactly, the 787 and even their own A350. Those planes offered point-to-point agility.
And that lack of agility is the core lesson here. The A380 required a maximum passenger load on almost every single flight just to break even.
Which is really hard to guarantee on a daily basis.
Right. If you couldn't fill those 500 seats, your profit margins evaporated immediately. So the aerospace report leverages this aviation history to critique the current trajectory of heavy lift scaling.
Are we building the rocket equivalent of the A380?
Precisely. Are launch providers building vehicles that are structurally incapable of being profitable unless a perfectly optimized massive payload is waiting for them on the exact day they're ready to fly?
Wow, okay, so let's test that theory against the current reality of the launch market. As of today, the roster of operational super heavy lift rockets that can actually hit that 50 metric ton threshold consists of exactly 2 vehicles.
That's right, just 2.
NASA's Space Launch System, which is a government exploration program, and SpaceX's Falcon Heavy, which is a commercial vehicle.
Yes, and the operational history of the Falcon Heavy provides a highly revealing data set for us to look at.
It is a striking data set. I mean, the Falcon Heavy was introduced in 2018 with immense fanfare. But according to this Space News piece from June 2026, it has only flown 12 times in 8 years.
With the most recent launch being back in April.
Right. So I have to push back on the industry's obsession with scale here. If the most powerful commercial rocket currently in existence has only flown 12 times in nearly a decade, doesn't that objectively prove there is virtually zero open market demand for massive rockets?
It certainly looks that way on paper.
Right. Like, why isn't the entire industry hitting the pause button right now?
Well, this raises an important question, and the aerospace study introduces a critical mechanical nuance here. This nuance prevents us from simply declaring the heavy lift market dead.
Okay, what's the catch?
It is tempting to look at those 12 flights and assume there are just no massive satellites that need launching. But the Falcon Heavy has a very specific architectural constraint, which it boasts massive weightlifting capacity. It's essentially 3 Falcon 9 boosters strapped together. But it utilizes the exact same payload fairing, the protective nose cone, as the standard Falcon 9.
Oh, wait, I see the problem. The physical volume inside the cargo bay is identical, even though the lifting thrust has basically tripled.
Exactly. You have this immense horsepower, but you are physically bottlenecked by volume.
Because satellites aren't just solid blocks of lead.
Right. Spacecraft, particularly communication satellites, are rarely dense blocks of mass. They are complex geometric structures. They have delicate folded antennas, massive solar arrays, optical payloads.
They need physical space.
A lot of it. You will almost certainly hit the volume limit of the Falcon Heavy's fairing long before you hit its mass limit.
So it's less like having a semi-truck with no cargo and more like having a heavy-duty, 1-ton pickup truck equipped with the bed space of a small hatchback.
That is a perfect analogy.
You have all the torque required to haul a massive load, but you literally cannot fit the cargo into the vehicle.
That perfectly illustrates the constraint. And this volume bottleneck is the primary engineering driver behind the next generation of super heavy lift vehicles currently in development.
They need wider rockets.
Exactly. They are not merely aiming to lift more mass. They are engineering significantly wider airframes, specifically to increase the available cubic volume for payloads.
Which brings us to the incoming fleet. We are looking at vehicles that just dwarf the Falcon Heavy. SpaceX's Starship is actively iterating. China is aggressively developing the Long March 9 and 10 vehicles.
And Blue Origin as well.
Right. Blue Origin, back in November 2025, announced the new Glenn 9x4. That's an upgraded configuration of their vehicle designed for vastly increased payload performance.
And this is where we must analyze the profit risks inherent in these massive launch vehicle infrastructure investments.
Because the scale is mind-boggling. I'm trying to visualize the financial exposure here. If we look at the capital expenditure, the CapEx, for something like Starship or the new Glenn 9x4, it feels less like building a new delivery vehicle.
What does it feel like?
It feels more like constructing a hyper-advanced high-speed rail network from scratch.
That is a highly accurate parallel.
Right. The upfront capital required for the specialized launch pads, the catching towers, the massive propellant depots, and the bespoke manufacturing facilities is just astronomical. You don't build a high-speed rail network unless you are absolutely certain you have Millions of passengers ready to buy tickets on day one.
Otherwise, you can't service the massive debt of the infrastructure.
Exactly.
And if the operational complexity we discussed earlier drives the marginal costs of each launch-up, the return on investment for the financial backers of these vehicles collapses.
It just falls apart.
To make the economics work, to offset that astronomical upfront capex, you need a relentless high-volume cadence of paying customers.
But as we just established with the Falcon Heavy, that open market demand does not currently exist.
It does not.
So here's where it gets really interesting. When you look at the findings of the aerospace report and overlay them onto the actual business strategies of SpaceX and Blue Origin, a very specific survival mechanism emerges.
Yes, they are taking a very different approach than legacy providers.
They are not building these giant rockets and hoping external commercial customers will magically appear to fill them. They are creating a closed-loop system. They are acting as their own anchor tenants.
It is a profound structural shift in the aerospace economy. I mean, historically, a launch provider operated strictly as a freight service for external government or commercial clients.
You built the rocket, the client built the satellite.
Exactly. But today, the organizations building the world's largest rockets are simultaneously building the world's largest satellite constellations. They're internalizing the demand.
And the primary driver of this internal demand is the emerging market for broadband mega-constellations. We're talking about networks like SpaceX's Starlink and Blue Origin's Project Kuiper.
Thousands of individual satellites.
Right, working in concert to provide global, low-latency internet coverage to you and me.
Yes. And what the report highlights is how this internalized demand directly dictates the engineering of the super heavy lift vehicles.
Because they are their own primary customer.
Right, so they can optimize the vehicle for a highly specific payload, driving incredible operational efficiency. The report points to Starship as the prime example of this. It features a highly specialized, slot-shaped payload dispenser.
Oh yeah, I have seen the schematics for that. It operates mechanically almost like a massive Pez dispenser for satellites.
Precisely like a Pez dispenser.
Yeah.
But consider the market implications of that design.
Okay.
If you were a traditional telecommunications provider building a bespoke, school bus-sized geostationary satellite, you cannot simply integrate your delicate hardware into a standardized slot designed for a flat-pack Starlink satellite.
It wouldn't fit.
No, and the acoustic environments, the vibration profiles, the deployment mechanisms, they're entirely optimized for the internal product.
Wow. So what does this all mean for you, the listener? It means the structural architecture of the most powerful launch vehicles in human history is currently being dictated by the deployment logistics of satellite internet.
It is a starkly pragmatic reality.
The grand, sweeping vision of interplanetary space exploration is functionally being funded, subsidized, and physically shaped by the quest for a global broadband.
The mega-constellations are the only payloads that currently possess both the mass and the volume requirements, combined with the sheer unit volume, to justify the flight cadence these massive rockets need to survive economically.
They're paying the bills.
Yes, but the long-term strategic ambition relies on moving beyond just internet routing.
Right, and the aerospace report attempts to map out what those future markets might look like.
If we connect this to the bigger picture, they identify long-term commercial avenues that could eventually require SHL capacity.
Like what?
The report specifically highlights the deployment of massive orbital data centers and the construction of space-based solar power infrastructure that could beam clean energy back down to Earth.
Wait, I have to stop here because this feels like a massive logical leap.
It is definitely a leap.
The report points to these markets, but outside of the broadband constellations, none of these other industries actually exist yet. There are no orbital data centers signing launch contracts today.
That is true.
And the space-based solar power sector is still largely theoretical and academic. We are basically building the most expensive, complex transportation infrastructure in human history to service a sci-fi future.
It's a huge gamble.
At what point do these speculative markets mature enough to actually drive the demand required to keep these SHL programs solvent?
That is the multi-billion-dollar vulnerability at the very heart of the industry. The report does not shy away from that exact discrepancy between current market reality and future demand.
They know it's a gap.
Oh, absolutely. Launch providers are essentially trapped in a delicate balancing act. They are attempting to build engineering marvels capable of revolutionizing our access to space, but they must balance that ambition against the brutal necessity of sustainable commercial success.
They cannot survive by merely building monuments to engineering. They have to operate a profitable, high-volume freight business.
And to achieve that profitability, to avoid the economic fate of the Airbus A380 we talked about, the aerospace report suggests something very specific.
What's that?
The maturation path for these vehicles requires establishing a regular, predictable, and remarkably boring launch cadence.
I find that fascinating, that the secret to unlocking the futuristic potential of spaceflight is to make it utterly boring.
It has to be routine.
Right. Before I can ever hope to see these building-sized rockets constructing orbital data centers or pushing heavy infrastructure toward Mars, they first have to prove they can do ordinary, repetitive, commercial grunt work.
Exactly. They have to operate with the reliability and economic predictability of a fleet of diesel delivery trucks.
The ordinary, repetitive deployment of internet satellites is the mandatory foundation that must fund the extraordinary.
It is the only viable path forward. The super heavy lift vehicle cannot exist as a technological novelty. It must be transformed into a proven economical utility.
And if it doesn't?
If the operational complexity of managing these massive vehicles on the ground makes that utility too expensive, the diminishing returns will cannibalize the profit margins. We will be left with a fleet of spacefaring A380s. Breathtaking in their scale, but economically unviable.
This has been a heavy but deeply necessary look at the mechanics of the future. We started by dismantling the ingrained assumption that scaling up a rocket automatically equates to better economics.
Right, the realities of heavy industry economics.
We explored the gritty mechanical realities of diminishing returns, where the sheer operational friction of managing cryogenic fluids and acoustics at scale can actually drive launch prices upward.
A harsh reality check.
Definitely. We looked at the Airbus A380 as a historical warning of how massive scale can destroy operational agility. We examined how the Falcon Heavy's low flight rate is heavily tied to a bottleneck of payload volume rather than mass.
The hatchback pickup truck.
Exactly. And we dissected the immense financial risks investors are taking on vehicles like Starship and New Glenn, risks that are currently only mitigated by the launch providers acting as their own primary customers to deploy internet mega-constellations.
It is a precarious ecosystem, and the economic variables are incredibly volatile.
Very true.
But I will leave you with a final, unresolved provocation drawn directly from the implications of this aerospace report.
Let's hear it.
We noted that future markets like orbital data centers and heavy space-based solar infrastructure do not currently exist. But if companies like SpaceX and Blue Origin successfully navigate the crushing financial risks.
Which is a big if.
Yes, but if they actually manage to operationalize these super heavy lift rockets cheaply and reliably, will the mere existence of that immense, affordable cargo capacity force those sci-fi markets into existence?
Wow.
Right. If they successfully build the capacity, will the market inevitably evolve to fill the empty space?
The ultimate orbital field of dreams scenario. Build the infrastructure, and the economy will manifest to utilize it. That is a brilliant framework to view the next decade of aerospace development through. Thank you for joining us on this deep dive into the true cost of scale. Keep analyzing the mechanics behind the headlines, and we will catch you next time.